Welcome back to our Chem 152 video series. In this problem, we'll be using a Ka value and a weak acid to find the pH of that weak acid. We'll begin with the weak acid H2S, and we are given a Ka value of 9.5 times 10 to the negative 8th. Our job here is to find the pH of a 1 molarity solution of H2S. In previous examples, you've used the equation pH is equal to negative log of H3O. Now for strong acids, you can go straight to this equation. However, for weak acids, we have a lot more math we have to do in order to find the pH. For weak acids, we're going to have to make an equilibrium chart or ice chart in order to find the H3O. The reason for this is because weak acids don't produce that much H3O, and we need to know how much we make before we try to use this pH equation. Now, if you aren't sure where to start, we can always try reacting H2S with water. This is a weak acid, so we'll draw the double arrow. And since we have a weak acid, we're going to lose an H, giving us HS. And weak acids become more negative, giving us HS minus. This means water will act as our base. Bases will gain H, giving us H3O positive. Now you can tell you're on the right track if you have a weak acid and it produces H3O or hydronium as one of your products. Any acid you have will create H3O as a product for the purposes of this course. Let's begin making our ice chart. Our initial molarity of H2S is exactly 1 molar. We will not write anything for water because pure liquids do not influence the equilibrium, and we are not given any initial molarity for HS negative or H3O positive, so we will write 0 for those. We know the H2S will go down by some amount, but we don't know how much, so we'll just say minus X. By the same token, the products, HS negative and H3O positive, will go up by at least a little bit, but we don't know how much of those either. What we do know is however much H2S we lose, we will gain an HS and H3O. At equilibrium, we will just add or subtract. Therefore, our equilibrium amount of H2S is 1 minus X. The others, we have 0 plus X and 0 plus X. We'll just write X here. Now, you may recall from a previous video about the small x approximation that we can sometimes make a shortcut in this calculation to reduce the amount of math we have to do. For the purposes of this class, you can say that if your k is less than 1 times 10 to the negative 4th power, we can cancel out any plus x's or minus x's. However, we must leave multiplied x's and lone x's alone. What that's going to change here is this minus x. We can safely assume this minus x will be very small compared to 1, and so we'll say since it's so small, it may as well be 0. This leaves just a 1 behind for our H2S. Then we can write the K expression. K is equal to products divided by reactants. Our products are X and X. We'll have X times X, and our reactants are 1. This gives us X squared divided by 1 is equal to our K. Since our K is 9.5 times 10 to the negative 8, we'll place the K in this position, and then we'll handle the algebra. We'll place our K into the correct position. When we do so, our X squared will be 9.5 times 10 to the negative 8th. Then to find X, we take a square root on both sides. This will cancel out the square, leaving just X behind. We go to a calculator and find the square root. We'll end up with 3.1 times 10 to the negative 4 molarity. Again, since our X was small, we can say that 1 minus 3.1 times 10 to the negative 4th is still very close to 1, so we can still just write 1. We can't do that with HS negative and H3O. We can just say that they are both 3.1 times 10 to the negative fourth. Now to find our pH, we have two options. We can say that pH is equal to negative log H3O. We can do this if we have an acid. If we have a base instead, we can say that pH is equal to 14 plus log of OH. Since we have an acid this time, and H3O is part of our equation, it makes more sense to use the first option here. We'll say that pH is equal to negative log of 3.1 times 10 to the negative fourth. Then we place it in a calculator. We'll end up with 3.51 for our pH. So this tells us that a 1 molarity solution of H2S will give us a pH of 3.51. You may also notice that H2S has two hydrogens to give, but we can safely assume that the second hydrogen is pretty much going to stay put. The first hydrogen is going to come off a lot more than the second one, so we will assume the second hydrogen doesn't make much of a difference to the pH. This won't be true for every acid, but for the acids that you see in Chem 152, that will work almost all of the time. Thank you for watching, and we'll see you again soon.